What does FEM stand for? F stands for finite, E stands for elements, and M stands for either methods or modeling. So what is FEM? It is a numerical technique or a methodology used to approximate solutions for complex engineering and physical problems. It decomposes an infinite continuum domain into a finite number of elements. So you are basically jumping from infinite degrees of freedom to a more solvable finite degrees of freedom. So what are some real world applications for finite element analysis? You could use this in aerospace and automotive industry. You can use this to study the stress and strains in the biological organs under extreme conditions. You could use to analyze buildings and structures. You can use this to model materials and manufacturing processes. You could also use this to develop protective equipment in defense and military applications. So overall, finite element analysis is a key tool in industries where precision, safety, and optimization matters. In this video, I will go over the terms required for someone to talk to another expert in finite elements. The first term here is discretization. So this is a process of breaking a continuous structure into a finite number of elements for numerical analysis. Discretization is the first step to solving real-world problems with finite element analysis. Next term is mesh. A mesh is a network of nodes and elements that discretizes a complex structure into smaller solvable parts for finite element analysis. Next term is node. A node is a point in the mesh where calculations occur. They connect elements to form the structure. Nodes are the foundation of the finite element mesh. An element is a small subdomain in the mesh connecting the nodes to approximate the structures. There are different types of elements. There are 1D, 2D, and 3D, and depending on the domain or the structure of interest, the elements are formed. They shape the precision of the finite element models. A degree of freedom represents an independent movement at a node. For 1D elements, it could be the translation in one axis. For 2D, it's two axis and sometimes rotation. 3D elements include the translation in X, Y, Z directions as well as the rotational degrees of freedom around X axis, Y, or Z axis. These define how a structure can deform under loads using mathematics. A shape function is a common term used in finite element analysis. This defines how a field variable varies within an element using nodal values. For example, an element is formed of 3 nodes and you have different displacements at each node. Shape function is basically an interpolation function that can estimate the displacements at any point inside the element based on the nodal values. These are extremely useful and converts the complex equations into a solvable finite element system. Then we look at stiffness matrix. Stiffness matrix is a mathematical representation of an element's resistance to deformation. It relates the forces and displacements in the FEM system at different nodes using the K equal to F formulation. This is the backbone for the finite element equations. Another term you commonly hear is the boundary conditions. They are basically constraints applied to the model to simulate real-world supports and interactions. There are different types of boundary conditions. There are Dirichlet boundary conditions, Newman boundary conditions, and mixed conditions. These boundary conditions define the finite element model's reliability and play a crucial role in finite element equations. The term loads in the context of finite element analysis is an external force, pressure, or displacement applied to the structure for a mechanics problem. For a thermal problem, it could be temperature or heat. That loads can be of different types. They could be point loads, distributed loads, static, dynamic loads, and it could depend on the physics as well. And they drive the real world response in finite element simulations. Another term you commonly hear in the world of modeling is convergence. This is the process where the finite element solution approaches the true value as the mesh is refined. This confirms your finite element model is trustworthy and credible. With this, we will stop the video. Again, why should you watch this video or follow this channel? The objective of this channel is to generate videos that can simplify the most basic, useful, and confusing concepts in the field of computational modeling, more specifically finite element modeling. We will try to make all the videos in a Q&A format and hopefully much shorter than this video, so that the focus is on a single question instead of trying to dump a whole lot of information on you. We will focus on those questions which are very important and crucial to consider when the FEA is actually applied for real-world applications. So let's go and learn what matters for real-world FEA applications. And thank you so much for your patronage of these YouTube videos. If you like the video, please like, share, subscribe, and comment so that we can provide more such videos to all the users. Have a wonderful, wonderful, wonderful rest of the day.